Howdy, class. Welcome back. This is the final installment, actually, for us right before the final exam. This will be the last video and cumulative review sheet. So I already worked it out with the answers to hopefully keep the length of the video down a little bit, and I'll just walk you through the solutions. That way, if you have any questions by looking up the answer key, hopefully you can refer back to this video and maybe it'll clarify it. But as always, if you have any questions, feel free to message me. I'll also be available all day Tuesday while you're taking your final. So if you have any, questions about anything logistically or anything like that, just feel free to shoot me a message on Edmodo and I can probably get back to you. Obviously not regarding any of the questions on the final though. All right. So just walking through the answer sheet here. First question is a trig graph question, modeling, using a Ferris wheel as our example. So you'll notice that it says you board at ground level and it's a 40-meter diameter. So we're starting at 0. There's no platform to walk up, and it goes 40 meters total. So because it starts at 0 and goes up to 40, we know the midline is going to be 20. So we can figure out the midline pretty quick, the average of the high and the low. And then the distance between the midline and the highest point, remember, that's always going to be what we call our amplitude. So the amplitude's got to be 20 units as well. It takes 4 minutes, it says, to complete one revolution. So being that 4 minutes, right here it says, is going to be the one cycle. It says we start in the 3 o'clock position, go up, down, and back to 3 o'clock position. It's going to take 4 minutes for that. So just reviewing that 3 o'clock position, that's as if you were in the Ferris wheel here. This is the 3 o'clock position. Here's 12 o'clock, 9 o'clock, and 6 o'clock. So in the 3 o'clock position, and it says you're ascending. So you're starting on the midline value, right? Here is the midline, and you're going up from the midline. That's why the graph looks like a positive sine curve, okay? They could also have said counterclockwise, same idea, okay? So we complete one revolution in 4 minutes. It says to sketch the graph for 2 complete revolutions and then returning to the boarding platform. So here's 4 minutes. Here's another 4 minutes for the second revolution. But now we're back to that beginning point at the 3 o'clock position. We have to go around 3/4 of a revolution to reach the boarding platform and actually get off. So that's another 3 more minutes. That's why it's a total of 11 minutes. Getting to the equation, it's just pumping in these pieces into our formula. So here's your typical sinusoidal model equation. And again, there's no horizontal shift here, so you don't need an extra parentheses with like an x minus c inside plus d. That'll come up later on. So here's our function, amplitude, period, midline. Frequency, but you use that from the period. And then the third question is what happens after 2 minutes and 45 seconds. So 2 minutes and 45 seconds, 45 seconds is 45 out of 60 seconds, so it's 0.75. So this would be 2.75 minutes. All you have to do is plug that in, use your calculator. If you plug that into your calculator, make sure you're in radian mode when you're evaluating it, right? Obviously the pi over 2 is in radian form. So it comes out to be about 1.5 meters. So again, 2.75 minutes, you'd be somewhere over here. Here's 4 minutes, here's 3 minutes. 2.75 minutes is somewhere right about there. So that kind of makes sense based on what the output is. All right, then we go down to question number 2. Here's your exponential functions question. So we've got radioactive decay. So remember, for all exponential expressions, you can say the percent remaining is equal to b to the t. That's a good place to start to get the effective annual rate of change, whether it's increasing or decreasing. This one is decreasing. So since there's only 40% remaining after 20 years, 0.4 equals b to the 20th. And then you solve that out by raising to the reciprocal exponent. So you get a b value that says 0.4 to the 1 over 20. You can use that expression in an exact form for your b, which can be written like this. Or you can approximate it to some decimals. Obviously, on the final exam, it'll tell you what to round any decimals to. So I've shown it out as a decimal approximation, but also you could write it as this or that. The next one says 25 years, how much will it be present? All you have to do is replace the 25 in for the t. So you could use any of these models. They'll come out to be approximately the same based on round-off error, obviously. So to the nearest tenth, any of these models would be satisfactory. You'll get 14.3 grams. All you have to do is plug in 25. And then the last one, what's the half-life? So again, remember this idea of percent remaining equals b to the t. For any half-life, it would be 0.5 equals b to the t. For any doubling time, it would be 2 equals b to the t. Tripling time, 3 equals b to the t, and so on and so on. So 0.5 equals b to the t. So we have that as our basic setup, just like here. Okay, we're trying to find the t, and we know the b value. That's the same one we used before. You could use any of these expressions. You'll get equivalent answers. I use the approximate decimal, and then I just take the ln of both sides. You can take any log if you like, but I'll take the ln, and we follow the log rules. The exponent goes out in front, and then you just divide by that constant. So you'll get approximately 15.113 years. Okay. Moving on to page 2. Here we have, we've done these questions now a lot recently. So, whoops. All right, so we just back out of that for a little bit so you can kind of see everything. So they give you this rational expression. It's not quite in standard form because this bottom is not distributed. So that would be a little tricky for the y-intercept. It looks like it might be 18 over 1, but you have to distribute the 5. So I did that over here, and we'll get to that when we get down to this part. But standard form is helpful for some things, and factored form is helpful for other things. So you kind of want to see the expression in both forms. So I factored this over here, and notice that you get a factor that's similar. Anytime you have a similar factor that can cancel, you create a hole in that function. So there's definitely going to be a hole at x equals -1 because of that factor. So it's helpful to rewrite the expression without the factor representing the hole in it. That way you don't get confused with extra x-intercepts or extra vertical asymptotes that aren't actually there. All right, so when we factor it out, we get this is the fully factored and simplified version, and this is the fully distributed version. So going through each of these pieces, the vertical asymptotes are all the factors that remain on bottom, right? That's here, after you reduce the hole. So don't include that as one of the vertical asymptotes. Remember, that's a hole. So we have one vertical asymptote at x equal 1. I drew it in orange. Then we have the horizontal asymptotes. Those come from the leading terms of the top and bottom. Just again, remember, you have to distribute the 5. So you see the 5x squared right there. 3x squared over 5x squared, so that's 3 over 5 when the x squareds cancel. And that's like 0.6. So I drew a 1 for reference. This would be just below 1. It's at 0.6. There's your horizontal asymptote. The x-intercepts are all the factors of the numerator set equal to 0. So x equals 6 or 6 comma 0. That's going to represent this x-intercept. That does not represent an x-intercept. Remember, again, that's from the whole. And then the y-intercept we talked about earlier, be careful about doing 18 over 1. That's not fully distributed. So it's actually 18 over 5. So 18 over 5 is about 3.6. And you can plug that in up here about, here's 1, so 2, 3, 3.6. So I put a dot in there. And then we get into, it doesn't ask about this in there, but I added it in down below. The whole is at x equal -1. We know that, but what's the y value? Another question could be like on multiple choice. What's the limit as x approaches -1? So you'd want to find out the y value. That's the same as finding the y coordinate of the whole, right? The point of removal discontinuity. So you take the fully simplified form and you plug in the x value from the factor that simplifies. So we're going to plug in -1 into this expression. So I did that over here. Here's your -1 plugged in for x, and you get 21 over 10 or 2.1. Which kind of fits in right where this would be curling through. So you can actually see that on your graph where it kind of fits in, you know, in that spot, okay? We go down to the solving equations questions, right? So 4 has 4 and 5 are 2 types of algebraic solving questions. All right, so the first one is a trig equation. It's got a Pythagorean substitution. I know that because I see a second degree trig expression with a different trig expression. So I can't solve, this is like having 2x squared equals y plus 3. That's no good. I have to have this all in one term, one type of trig function. So on the side, I wrote down on the side over here, recall the Pythagorean identity, sine squared plus cosine squared equals 1. Right now, you may not have memorized any of the other versions, which is fine, but you can always create the other versions by dividing by something or moving these terms to the other side. So, but I divided by sine squared because I know when I have 1 over sine squared, that's where I get a cosecant squared from. So sine squared over sine squared is 1, cosine squared over sine squared is cotan squared, and 1 over sine squared is cosecant squared. So now I have a replacement that I can substitute back in over here. And what that will do for me is it will turn the equation entirely into cotangent expressions. So it's a second degree cotangent expression, which means I'm going to have to factor it or use a quadratic formula eventually, but I can distribute this 2 and then set it equal to 0. So I minus the 3 and minus the cotan over. write it in standard form, and then this is something that I can deal with. It's got one term cotangent in it. It's a second degree. You can either factor it, if it does factor. It's possible that it might not. Or you could just go right to the quadratic formula if you don't like factoring with leading coefficients. You do that bridge technique, and then you separate it by factoring by grouping. Anyway, this breaks down into these two factors if you want to attempt it that way. If you do the quadratic formula, you'll get these two values anyway, -1/2 and 1, so you get the same two values by the quadratic formula. But those are for cotangent, remember. So to get my angles, I don't really want to use cotangent because it's kind of hard to use the calculator. But I can do the reciprocal of that. So if cotangent is equal to -1/2, tangent is equal to -2/1, just reciprocate. So I know that the tan of theta has to come out to equal -2. And over here, if you reciprocate 1, you still get 1. 1/1 is still 1 when you flip it. So tan of theta equals 1. This is the easier one because it's a special trig value. So when tan of pi/4 as a reference angle comes out to +1, that's one of the values on your chart. I know that it has to be a pi/4 reference angle, but because it's positive, it's in quadrants 1 and 3. So pi/4 in quadrant 1, and then pi plus pi/4 in quadrant 3. So I'm going to go around to pi and then plus pi/4. So that's 5 pi/4. Over here, 2 is not one of the exact values that we have, so it's not going to be a special angle value. But we can just leave it as arc tan 2, or what we call inverse tan of 2. Remember, we don't use negatives with our reference angles, right? So that's just going to tell me where to go. So inverse tan of 2 is the angle, right? And if it said round your angles to the nearest decimals, you could use a calculator and type in second tan 2. You'll get a decimal value in radian form. But this is not really asking for that, so you can just leave it in an exact form. It's less work for you. You don't have to even use your calculator. So inverse tan of 2 is the reference angle, but I have to place it where it's negative. So quadrant 2 and 4 are where the tangent function is negative. So if I have inverse tan of 2 as my angle, just like pi/4 could have been a reference angle, in the second quadrant, it's going to be pi minus that reference angle. And then in the fourth quadrant, it's going to be 2 pi minus that reference angle. And those are exact answers. But again, like I said, you can always, if the question required to get to nearest decimal values, you could always plug that into a calculator. Okay. Then on the bottom one, we have a log equation. So you can't solve multiple log expressions on one side of an equation to begin with. So you can't do like 3 to the 3 to the 3 to the, that would be incorrect algebraically. So you have to combine these into a single log expression. So when you have subtractions of 2 logs, that's like combining into one big quotient under that same log base. So this reduces from here. So I combine that. And then I want to get rid of this log expression on the left. So we use the base of the log as a base on both sides. The base to the log of that base are inverses, so they're going to cancel out. And then we just have to apply that base on this side. So x plus 6 over x minus 2 equals 3 squared, which is 9. And now it's just a simple cross multiply, and you can solve it out for x. At the end of the road, just be careful. Make sure you check, right? Sometimes you'll get more than one answer. This came out to be a linear expression. Sometimes they'll be quadratic, so you'll get 2 answers. Make sure that the answers go back. When you substitute them into the inputs of the logs, you don't create any zeros or negatives. It has to be a positive input for a log. Okay, so when you plug 3 in, 3 plus 6 is 9, that's fine. 3 minus 2 is 1, that's fine. You just can't have 0 or negatives as inputs for logs. Okay. All right, final page is, can you graph a couple of these things and find the equations? All right, so the first one's a quadratic. So we know if you're given the vertex of a quadratic, you would start with vertex form. If you're given the roots of the quadratic, you'd probably use the factored form. So that would be like a times x minus root 1 and x minus root 2. But in this case, we're given the vertex, so we can use vertex form. We're going to plug that vertex in. Remember, the x-coordinate changes the sign in the factor. The y-coordinate stays the same outside. So we start out with this, and we just have to get that missing a value. So how do we get that a value? This is how we get it. We substitute in any other coordinate, which we're given here, and you substitute in for x and for y, and then we work it out from there. We get our a value. It comes out to be -1/8, which makes sense, again, because it's upside down. So the negative leading coefficient kind of jives with that. All right. Then we go down to the bottom one. This one we have multiple answers, actually, that you can have. I showed one of them based on where I highlighted one cycle to be. in my estimation, it makes it's a little easier to identify the minimum and maximum landmarks than it would be to identify the midline landmarks, where you would use a sign function to write the expression for. Only because the midline expression landmarks, they don't hit exactly at integer values. They're going to be in between boxes. So since these hit right on integers, they were a little bit easier to identify. So I highlighted one cycle of a negative cosine curve. But there, again, down here, I wrote a little note. There are other answers that you could have as well based on changing the horizontal shift and changing the type of function that you pick. So let's start off with a couple things. We know the max is 4, the minimum is -2. So then we can average that out and get the midline. That's 1. That's the average of the high and the low. So add these up, divide by 2, you get your midline. And then we can determine the amplitude, which is the distance from the midline to the highest point. So from 1 to 4, it's going to be an amplitude of 3. So right now we have the midline is 1, the amplitude is 3. Midline goes here, amplitude goes here. All right, so now the next thing is, well, I highlighted one cycle right here from minimum all the way to next minimum. That's one cycle. You could also do maximum to the following maximum. That works also. You can do midline to every other midline. But again, since they're not on integers, I didn't choose to do that. So from minimum to minimum, we go from 2 to 8. That's going to be a period of 6. So the period is definitely 6 units. That's what I wrote right here. And then we can get the frequency from that by just using that good old formula. 2 pi over the period is the frequency. So pi over 3 is going to be your frequency for this. Now comes, since it doesn't start on the y-axis at one of the landmarks, I'm going to have to employ a horizontal shift. So because I highlighted the negative cosine function right here, I'm going to choose to shift over to that spot. That's going to be my starting landmark. So I need to move this graph 2 units to the right so that my negative cosine curve, which would normally start right here and go up, I need to push it over to the right 2 units. It's as if you're sliding the y-axis to start right where your landmark is. So I need to slide that y-axis 2 units to the right. So that's why I have this horizontal shift up here employed to the right 2. So putting all of this information in, we have y equals I chose a negative cosine curve, has an amplitude of 3, frequency of pi over 3, employ the horizontal shift, make sure you have double parentheses with that, and then midline shift on the outside plus 1. Okay, so that's everything, guys. Hopefully it was a good summary with the 3, review sheets. Final exam will be released at 8 a.m. Tomorrow on Tuesday, and you'll have all the way through the next day, Wednesday, by midnight, 11:59 p.m. to submit. So you'll have the assignment up. It'll be sent out through Edmodo. I'll have the file also posted on my website as well, in case it's easier for you to access it there. All the directions will be included in the assignment, so it'll be clear. There's going to be an answer sheet that will kind of aggregate all of your answers together into one spot, just to make it a little bit easier for me for grading. It'll be 25 multiple choice along with some free response questions. So the answer sheet will have the opportunity for you to put all of your answers onto that one page. If you have any questions, just message me on Edmodo, and good luck with the final, guys.